11.8 power series. Power series is why series are interesting and useful and important. Okay, I've alluded to this, but now we're going to start looking at why exactly they are important. It has to do with the fact that a power series is now a function of x. It actually has a variable in it, but it's an infinite series. Okay, so what we're going to end up doing with power series is we're going to represent known functions that may be ugly, complicated, hard to integrate, hard to differentiate, just nasty suckers. And we can get really complicated functions that we can represent as a power series, as an infinite series of functions. Okay? And once we do that, it's a whole lot easier to work with the series and do calculus on the series and analyze the series than it is to work with the nasty function that we started with. And what this does, not only does it allow us to handle nasty functions that we already know in a new way, it allows us to create new, much more interesting, much more complicated functions than we've ever had to work with before. It doesn't seem like that's a good idea, but actually that becomes a more powerful tool mathematically when we no longer restrict ourselves to these things like continuous functions. We like continuous functions because they're easy to work with, but they're also very limited in what they can do mathematically. We end up looking at things that have more applications than we've ever had before. So let's start off by defining what a power series is. The next question will be, when do they converge? And then the last question is, how do we represent a function that we know as a power series? How do we find the equivalent power series for a given function? And that's where we run out of time for the semester, and I have to start up next semester. So a power series it actually just sounds cool. We've been talking about series, but now we're talking about power series.
You have to say it like that.
Power series, yes.
Every time you say it, you have to say it like that.
Take the sum from n equals 0 to infinity of some constant c sub n times the variable x to the nth power. This is the general form of a power series. I can't do that all day long. I think that maybe is true.
That would be so good.
Camacho from video. All right, so c sub n, these are like the normal a sub n terms like we've been working with, but now we've got a variable, an x, where we're going to be able to plug in a number. So this is now a function of x. Okay, if I write out the terms of the series, it looks like this. It's c sub 0, x to the 0. Now, anything to the 0 power is just 1, so there's no x in the first term, but the second term would be c1 times x plus c2 times x squared plus c3 times x cubed plus c4 times x to the 5th plus and so on. So again, x is the variable. The c sub n's are constants, which just like we would with a polynomial, we call them coefficients. In fact, that's a very good way to think of these things. This is like a generalization of a polynomial, right? Because a polynomial would be like if I stopped somewhere. In fact, the partial sum of a p series is a polynomial. But now, of a power series. A power series now goes on forever. It's like a polynomial of infinite degree that never stops. Okay? So the CNs depend on n, but they don't depend on x. And so when we start looking at some of these power series later on, like this one down here, what you'll see is that the c sub n has a formula that depends on n, and then you've got an x to the n power in each term. Okay? So the power series has different values, that is different outputs, for different values of x. If I said f of 1, that would just be c0 plus c1 plus c2 plus c3 plus c4. Right? I mean, just think of that over here. F of 1 would be c0 plus c1 plus c2 plus c3 plus and so on. F of 2 would be c0 plus 2c1 plus 4c2 plus, that's 1, 2 to the first, 2 to the second, 2 to the third, C3, and so on. So notice, whatever value you plug in for x will change which series you're talking about. And the series may converge or diverge for different values of x. So the same series could be convergent for one value of x and divergent for another value of x. In fact, the main goal of 11.8 at the end of this section is to answer the question of, given a power series, what values of x does it converge for, and what values of x does it diverge for? That's the ultimate goal of today's lecture. Let's get familiar with these a little bit by working out and comparing to this first series. If I were to plug in the numbers, looks like this. It's 1 over 1 to the fourth, plus 1 over 2 to the fourth, plus 1 over 3 to the fourth, plus 1 over 4 to the fourth, plus so on. Which means this is a constant series. It's not a power series, it's a constant series. I don't usually use the word constant, that's implied. So if I say series, I just mean infinite series. If I say power series, I mean one that has a variable in it of the form we wrote above. By the way, can you tell me, does this one converge or diverge? Just by looking at it, do you know? I hear it converges. Why? It's a P series. I went over into the fourth. That's squared. What do you?
Always comparing it.
Oh, so yeah. Well, you compare it to 1 over n squared, and it's always smaller than 1 over n squared. So you could do that, but you don't need to do that. If you have 1 over n to the p, remember, all you got to do is check the p. If it's bigger than 1, converges. If it's less than or equal to 1, diverges. So this one converges by the p-test. Now this one, on the other hand, would look like 1 over 1 to the fourth times x to the first plus 1 over 2 to the fourth times x squared. I'm just plugging in the different n's, n equal 1, n equal 2, 1 over 3 to the fourth, x to the third, plus 1 over 4 to the fourth, x to the fourth, plus, and so on. This is a power series, and it may converge or diverge depending on x. Now, I don't want to do it with this series yet, but in a minute we're going to come back and talk about how we determine whether or not it diverges or converges in general, how we find those sets of x. In fact, that's the example down here. For what values of x does the power series below converge? So we'll come and look at that in just a second. Before I do that, I do want to give you that there is, in fact, one other way of writing the power series. It's a more general version of the power series. The only difference now is that instead of raising x to a power, you do from the sum equals 0 to infinity of still the coefficient c sub n, but instead of x to the nth power, you do x minus a to the nth power. So in every term, instead of having x to the 0, x to the first, x to the second, x to the third, you have x minus a to the 0, x minus a to the first, x minus a to the second. And a is going to just be a parameter that you can set. So you call this a power series in x minus a, or a power series centered at a. I'm going to write out a few terms. Yeah, and I did say this. Centered at a. This would look like C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed plus and so on. I'm going to highlight a few things just so you see where all the pieces are. You've got a set of coefficients in every term, and because this is, I'm just giving you a general definition, I'm writing them in as the C sub 0, C sub 1, C sub 2. In general, they may be defined for you like this n factorial down here, right? There may be a formula, or there is a formula for the C sub n's, okay? And then you've got the, I guess, the polynomial part of this, which is the x minus a squared, x minus a cubed, and that term just keeps getting bigger and bigger in terms of its degree. Okay? So, whereas up here, in fact, you can see this is a special case of this, right? What value of a do I plug in to get this? Well, if a here is 0, in fact, I'm going to come back and draw a line up here. This one is centered at 0, right? Because x minus 0 is just x, right? You could think of this as C0 plus C1x minus 0 plus C2 x minus 0 squared plus and so on, right? That's the same terms there. Okay. So this is now just, like I said, more general version of it. The question now is, where does this thing converge? For what values does the following series converge? And I'm going to start, I'll give you a general technique in a second, but let me just explore a couple of things right off the bat here. I want you to consider, what if, simple case, x equals 0? In fact, this is going to always be true for any series. If you plug in the center of it, this where it's centered, and since this one's not x minus anything, we think of it as centered at 0. Notice what happens when you plug in 0, right? Sum n equals 0 to infinity, n factorial of 0 to the nth power. So what is every term of that series equal to? And if you add up an infinite number of zeros, you get 0, right? Or a better way to say that is, if you look at the sequence of partial sums, right? Take 0, and then add to that 0, you get 0. And then add to that another 0, you get 0. What's happening? You're staying at 0, so you're converging to 0. So it converges. So the first thing you know is that it converges at the center. In this case, it converges at 0. All right, so what about if x is not 0? I'm going to suggest, and most of the time this is going to be what we do, use the ratio test. Not 100% always, but most of the time, 99.9% of the time, the ratio test is the right choice. Actually, it's probably more like 98% of the time, but who's counting? Do you remember the ratio test?
Absolute value of a sub n plus 1 divided by a sub.
Exactly. We're going to take the limit of that as n goes to infinity. And before we do it, let's remember, what does this tell us? Like, if we get a number out of this, then what does that number tell us?
Greater than 1.
It's bigger than 1,
Diverges.
diverges. That's correct.
It's less than 1.
Less than 1,
It's absolutely convergent.
it's absolute convergence, and if it's equal to 1,
John Snow.
you know nothing. And in fact that you know nothing means you have an extra step at the end of our problems, because we're going to have to figure out what happens at those endpoints. And I'll tell you what I mean when I get there. But first of all, again, we're trying to find the number. So we're going to say if this thing that we get out of this limit is bigger than 1, it diverges. It's less than 1, it converges. In fact, what we will do in general, since there's going to be an x in this, is set it less than equal to 1 and say what values of x make this limit less than 1. All right, so what's the n plus first term look like in our case?
N plus 1 factorial x to the n plus 1 over n factorial x to the.
I'm going back to the original series, and I'm just plugging in n to plus 1 and n. And then I'm going to simplify that. Limit as n goes to infinity. The x's, x to the n, cancels and leaves just x to the first, which is just x. Now, since x could be positive or negative, I actually have to keep the absolute value this time. Okay? What's n plus 1 factorial divided by n factorial?
It's factorial. 1 factorial. Because if you distribute each, you get n factorial. No, it's n plus 1.
N plus 1 times n factorial over
It's just n plus 1.
n factorial.
Not always.
Right, because n factorial just means multiply all the way down to 1. And since n plus 1 times the next thing lower is n times everything down to 1, then I could just write that n everything down to 1 as n factorial, and they cancel, and so you end up with just n plus 1. All right, what do you think the limit as n goes to infinity of n plus 1 times x does? Now think of x as a fixed constant. You can plug in different numbers into it, but for any value of x, this thing stays the same no matter what n is, right? So think of x as a constant. What's happening to n plus 1 times a constant as n goes to infinity? Bigger and bigger and bigger. In fact, it goes to infinity, okay? Since x is a constant with respect to n. I mean, it's a variable because we can plug in different numbers into it, but if I'm taking the limit as n goes to infinity, x isn't changing. So this thing, I'm just multiplying a bigger and bigger number times whatever x is, right? Even if x was really small, like 0.0001, but it doesn't change, and I keep multiplying by bigger and bigger n's, still the whole thing goes to infinity, which, by the way, is bigger than 1, which means diverges. So here's what we know. I'm going to write this at the very bottom of the page here, okay? The power series, n factorial x to the n, converges if x equals 0 and diverges if x is not 0. So the only place where that series converges is when x is at its center. Okay. Let's do another one. For which values of x does the power series below converge or diverge? Now, I'm not going to go through the steps of checking it, but it should now be obvious to you that for absolutely sure this thing will converge when x is 3. Right? Because it's 0. Right? So I'm not even going to say that anymore. I'm just going to assume that I know that. Let's use the ratio test. Actually, we don't have to use the ratio. This is that one of the very small times when we'll get away with not using the ratio test. And really, the only time you never use the ratio test is if your coefficients are a constant. Just think about what this looks like if I plug in n equals 0, n equals 1, 2, so on. This looks like, plug in n equals 0, you get x minus 3 to the 0, which is 1, plus x minus 3 to the first, plus x minus 3 to the second, x minus 3 to the third, x minus 3 to the fourth, plus so on. Actually, you could use the ratio test and it still works. To me, there's an even shorter way. What do you notice about this series? Do you recognize what kind of series it is? Not just power series. It's geometric. And the R is x minus 3. Now, when does a geometric series converge? Other way, less than. Yep. So absolute value of R less than 1, which means the absolute value of x minus 3 has to be less than 1. So as long as the x that you plug in, subtracted by 3, in absolute value, is less than 1, then this thing converges. Now, I prefer to write these in interval form, so what I'm going to do is solve this inequality. Have you solved absolute value inequalities before? Well, you could rewrite this as x minus 3 is less than 1 but bigger than negative 1. That's a little trick we learn in algebra. These two are equivalent statements. This one, absolute value of x minus 3 less than 1, is the same thing as saying that x minus 3 is bigger than negative 1 and smaller than positive 1, right? And then to solve that for x, add 3 to all three sides. You get x is smaller than 4 and bigger than 2. Okay? Or the interval notation, I would write it as the interval from 2 to 4. There are two results we've seen so far. One where it only converges at the center, one where it converges on the interval. It's also possible, I'm not going to do an example, actually we'll see one later, where it converges no matter what x you plug in, converges everywhere. Those turn out to be the only 3 possibilities ever. For a power series, you get 3 possibilities. So that's what this theorem right here says. That for a given power series, centered at A, so you got coefficients times x minus a to the n. So this infinite polynomial, there are only 3 possibilities for when the series converges. It either converges only when x equals a, only at the center, and diverges everywhere else. Okay, it could converge for all x, any real value of x that you plug in. I don't know, this is a typo. The series converges for, the last possibility is that there's some interval where it converges. And I'll write it like I have it written up here. So it's like x minus a less than r. So it converges within some r of a. Notice, by the way, this is the same, I'm going to write this in a different color, but this is the same as saying x is between a plus r and a minus r. So inside that interval, from a minus r to a plus r, it converges, and outside of it, when that's bigger than r, it diverges for some r that we're going to call the radius of convergence. So when talking about power series, that's going to be one of the first questions we have to answer, is what is its radius of convergence? And in fact, there's another thing that we call the interval of convergence, and that's what I was talking about up there. There are actually 4 possibilities of what happens on the boundary of the interval of convergence. Down at the bottom of the page, before I write in 1 through 4, draw this picture for me. Think of the real line right? This is all real numbers. Put A at the center. Now what I'm going to do is I'm going to go some distance out from A equally on both directions. So this distance here is R, and I'm also going to go this distance here. Okay? Which makes this point right here A plus R, this point over here A minus R. Okay? And you can do this by just shading it, but inside here, we're saying it converges. And then outside of there, I'll do this in purple for like a red, it doesn't work out there. Outside there, out here, and out here, it diverges. So when we're plugging in different values into the power series, something happens out here where it diverges inside here. That series will be convergent, which means I can plug in numbers and get a number out of it. But what happens at the endpoints, we have to check separately. So put a little note here, check endpoints. Because you could have now 4 possibilities of what the interval of convergence will look like. It could go from A minus R up to A plus R and not include the endpoints. What I mean by that is if I plug in A minus R, if I plug in the left endpoint of this interval into my X, it could diverge. And I plug in A plus R in for X, it also diverges, okay? So this means diverges at endpoints. You could have where it converges at the left endpoint and diverges at the right endpoint. So converges at left and diverges at right endpoints. You could have that it diverges at the left endpoint and converges at the right endpoint. Or you could have the last possibility, A minus R, all the way up to A plus R. Right, in interval notation, putting a bracket means it's included in the interval, so it converges at endpoints. So those are your possibilities. So on the following examples, the rest of this section, I'm going to give you a power series, and you have to find the radius and the interval of convergence. The steps to do that are to use the ratio test and to find the values of x that make the ratio test show convergence. And then you've got to check your endpoint. So let's do a few examples of that to get the hang of it. I'll give you a chance to catch up writing there real quick. All right. Find the radius and interval of convergence for the following power series. Step 1, use the ratio test. So again, a sub n plus 1 over a sub n. Plugging in n plus 1 for the n's, you get x minus 1 to the n plus 1 divided by n plus 1. All of that over x minus 1 over n. There's an n right there. Invert and multiply x minus 1 to the n plus 1 over n plus 1 times n over x minus 1 to the n. So what do you get?
X minus 1 to the n times n over n plus 1.
Just X minus 1.
You have n of them down here.
Oh, yeah, it's the first.
Alright, so that cancels with all of these. And you have n over n plus 1, and then just an x minus 1 to the first left. Alright, can you take the limit of that? That's pretty easy, isn't it? The constant is just a constant, so it just sticks around. So it's like x. In fact, what does this do as n goes to infinity? Doesn't get small. Actually, it keeps getting bigger. On top gets big, the bottom gets big. But you could use your Bobo Bodden needs DC on it if you wanted to. Goes to 1. Dominating term on top is n, on bottom is n, so you get n over n for large n, so it goes to 1. Or eats DC means exponents are the same, divide coefficients. 1 over 1 gives you 1. So all that's left is the absolute value of x minus 1, because that's the constant with respect to n. All right, so what has to be true for this to converge? This is the L from your ratio test, right? It has to be less than 1 to converge. So you set this less than 1. Okay? From the ratio test. Okay, which by the way means x minus 1 is between 1 and negative 1, which means x is between 0 and 2. So your interval is 0 to 2, but you don't know what happens at the endpoints. Okay? What about the endpoints? So here's where you've got to take an extra step. So we use the ratio test, we take the limit of it, we set it less than 1, solve that inequality for x, and now we know what the interval is. It's from 0 to 2. By the way, what's the radius of convergence? This right there is your R. Okay.
Which one is that, or?
It's the one right here. So if you go back up to my picture from here, it's how far away you are from the center, right? So your center in this case is what? 1, right? And you're saying all values within 1 of 1, right? Absolute value of x minus 1 is less than 1. So there's your radius of convergence. But what I really want to know now is the interval of convergence. And I'm close. I've got 0 to 2, but I don't know what happens at 0 and what happens at 2. So the last step is to just plug those two numbers in, one at a time, into your power series, and then go back and use the tests to figure out what happens to that constant series now. So let's let x equal 0. So plug in 0 up here, what do you get? Oh, and that starts at 1, by the way. 1 to infinity. Negative 1 to the n over n. Does that converge or diverge? Well, we've got to use one of our tests. It's the alternating series test. So if you ignore the negative 1 and just look at 1 over n, it has to be decreasing and go to 0 to converge. Does 1 over n decrease and go to 0? Right, b sub n in this case is 1 over n.
Just 1 over n now.
1 over n. As n goes to infinity, what does that go to? The bottom goes to infinity.
0 goes to 0. It's
1 over a bigger and bigger number, 1/2, 1/3, 1/4, 1/5, 1/8, 1/10. It's to the, yeah, so it's a p series if there's no negative 1 up here, right? In fact, what I'm saying here is that because of the negative 1, the alternating series test says all you have to check is, does it decrease and does it go to 0? If that's true, then the alternating series converges.
Okay.
Converges by the alternating series test. Does that make sense? We're going to apply the alternating series test. Since it goes to 0 and it's decreasing, it converges. So I know this. What about at x equals 2? You plug in 2 here, 2 minus 1 over n is just 1, right? 1 to the nth, which is just 1. Now, what does this series do? By, why is the reason? P-test. Because P is equal to 1, anything less than or equal to 1, it diverges. So what goes on the 2? Parentheses, okay? So your interval of convergence is from 0 to 2, including 0 but not 2. And your radius was r equals 1. All right, I've got a few more examples, at least I guess 2 more examples I need to do, but I'm out of time, so I'm going to stop there. We're going to come back and look at this thing called the Bessel function, which is used in a lot of higher level analysis courses. But checking interval and radius of convergence is the same steps we just did.
Just go back to that real quickly? Yeah, just go back up.
There you go.